Learn like a pro.
All right, let's dive into a core chemistry question that on the surface seems to make absolutely no sense. Why are some metals so dramatic while others just sit there?
You know what I mean. You've probably seen those videos of a tiny piece of potassium hitting water and just exploding in a flash of purple flame. It's wild. But then you think about, say, a copper statue that's been outside for 100 years. It does pretty much nothing. It seems totally random, right? Well, it turns out there's a secret order to all that chemical chaos.
And that secret is basically a power ranking for metals. Think of it like a league table that tells you who the most aggressive players are and who's just happy to sit on the sidelines. So this chemical league table has a proper name, of course. It's called the Reactivity Series. Let's pull back the curtain and see what it is, and more importantly, how it's built. At its heart, it's just a list. It's a list that puts metals in order based on how intensely they react. Simple as that. The higher a metal is on this list, the more likely it is to, cause a scene. So here it is, the series itself. Way up at the top, you've got our superstar, potassium. He's the most reactive of the bunch. And then you go all the way down to the bottom, and you see silver, which explains why your silver ring doesn't burst into flames when you wash your hands. Now, you might notice two oddballs in there, carbon and hydrogen. They aren't metals. But trust me, they are super important reference points, and we'll see why in a bit. Okay, so how did chemists figure out this order? They didn't just draw names out of a hat. No, they did what scientists do best. They ran experiments and watched what happened. The big three tests are reacting metals with cold water, with steam, and with acid. And this first test with cold water just perfectly shows the top of the food chain. You drop potassium in, you get a literal explosion and a flame. Sodium goes wild, calcium gets pretty bubbly, but then you get to magnesium. And it's a very slow, almost boring reaction. And anything below magnesium, like zinc or iron, absolutely nothing. The evidence is crystal clear.
But hang on a second, what about magnesium? We just called it boring. Well, this is where it gets interesting, because conditions matter a lot. Take that same unreactive magnesium and hit it with steam instead of cold water, and it suddenly wakes up, reacting super fast with this brilliant white flame.
And this table really paints the full picture. For the big guys, potassium and calcium, it doesn't really matter. Cold water or steam, the reaction is going to be violent. But for magnesium and zinc, that extra energy you get from steam is like the key in the ignition. It unlocks their reactivity and lets us figure out exactly where they belong in the rankings. All right, next up, the acid test. This is how we sort out the metals in the middle of the pack. Again, it's all about observation. Drop in magnesium, and it fizzes away like crazy, making tons of hydrogen bubbles. Zinc is a bit more chilled out, with a nice steady stream of bubbles. And iron? It's pretty slow. The faster the bubbles, the higher the reactivity. And that brings us to a neat little chemical puzzle. If you look at our list, lead is definitely above hydrogen, so it should react with acid and produce hydrogen gas, right? But when you actually do it in the lab, it starts bubbling, and then it just stops. What on earth is going on? The answer has a fancy name, cassivation. What happens is, the first little bit of lead that reacts creates this stuff called lead-2 chloride. And here's the key, it's insoluble. So it forms this thin, white, waterproof jacket right on the surface of the lead. This coating acts like a shield and physically stops the acid from reaching the rest of the metal. So the reaction basically just smothers itself. So we've seen what happens. We've seen the evidence. But now for the big question, why? What's going on at the atomic level that makes one metal more reactive than another? Well, it all boils down to a fight over electrons. So here's the golden rule, the most important takeaway. When we say a metal is reactive, what we really mean is that it is very eager to get rid of its outer electrons to become a nice, stable, positive ion. The easier it can ditch those electrons, the more reactive it is. And there's no better way to see this than in something called a displacement reaction. Let's look at the classic example. You take a strip of zinc metal and you dip it into a beautiful blue solution of copper sulfate. Two things start to happen right away. First, that blue color, which comes from the copper ions, starts to fade. And second, you see this brownish solid coating the zinc strip. That's pure copper metal. What happened? The more reactive zinc literally kicked the copper out of its own solution and took its place. So this is the heart of it, the actual electron swap.
Because zinc is more reactive, its atoms want to lose 2 electrons more than the copper ions want to keep them. So a zinc atom gives away 2 electrons, that's called oxidation, and turns into a zinc ion. At the exact same time, a copper ion from the solution grabs those 2 electrons, we call that reduction, and turns back into a solid copper atom. And this whole idea of one thing losing electrons while another gains them is called a redox reaction. It's short for reduction and oxidation. And it doesn't just happen in solutions. If you take iron powder and heat it up with black copper oxide, the same thing happens. The more reactive iron steals the oxygen from the copper. The iron gets oxidized, the copper gets reduced. It's the exact same game of swapping electrons. Okay, so this is a really powerful tool for chemists. But how do we actually use it? Well, the Reactivity Series is amazing for predicting how reactions will turn out, especially in big industrial processes, like getting pure metals out of the rocks they're found in. And this is where those 2 nonmetals, carbon and hydrogen, come back into play. If you want to get copper from copper oxide, you can use carbon, because if you look at the series, carbon is more reactive than copper. It can win the fight for oxygen. For lead oxide, even hydrogen is reactive enough to do the job. But what about magnesium oxide? Nope. Magnesium is so far up the series, it holds onto its oxygen so tightly that neither carbon nor hydrogen is strong enough to pull it away. The series can also tell you how stable a metal's compounds are. Take sodium. It's super reactive, right near the top. That means its compounds, like sodium carbonate, are incredibly stable. You can heat them up like crazy and nothing happens. But calcium is a little less reactive, so its carbonate is less stable. If you heat it up really strongly, it'll break down. So here's the rule. The higher the metal on the series, the more stable its compounds are. Okay, that was a pretty deep dive into the theory and how we use it. So let's wrap this all up with a couple of handy tools to help you really master the Reactivity Series. Trying to remember the whole order can be tough, so chemists have come up with silly sentences to help. Here's a popular one. Please stop calling me cool, zebra, I like happy, cute ant. Each word starts with the letter of the element. And yeah, ant for silver is a bit of a stretch, but hey, whatever helps you remember it, right? And let's bring it all together for those top contenders one last time. This little table summarizes everything perfectly. You can really see that clear trend, from explosive potassium all the way down to magnesium being super slow in cold water. And it highlights that really important point about magnesium. It needs that extra kick from steam or acid to show its true colors. So I'll leave you with a real-world puzzle to think about. A big ship is made of steel, which is mostly iron. We know rust is just iron reacting. Now, knowing what you know about displacement and this constant battle for electrons, how could you use a more reactive metal, maybe something like zinc, to protect that massive steel hull? How can you make the zinc rust instead of the iron? It all comes back to that electron swap. Thanks for tuning in.